Welcome to the final edition of Standing on the Shoulders of Giants. This week we're looking at the future of astronomy. Over the last 22 weeks of Standing on the Shoulders of Giants programs, we have explored some of the great discoveries that have shaped astronomy over the past century and learned the stories of the many heroes who have helped make these discoveries happen. From groundbreaking new theories to serendipitous discoveries, from crafting the world's best telescopes to designing a way to detect gravitational waves. Our astronomical knowledge has grown by leaps and bounds thanks to the efforts of famous names, unsung heroes, and immense teams of scientists who have dedicated their careers to better understanding the cosmos. In the coming years, we're facing a burst of incredible innovation in astronomy. Tomorrow's hero of astronomy are hard at work today working on new telescopes that have been decades in the making and laying the groundwork for astonishing new discoveries that will continue to change how we see the universe. In this final program, we're going to look at some of the exciting future developments in the field, the potential discoveries this work could offer, and what it means for the next generation of heroes in astronomy. At the beginning of this series, if you remember, we divided it into 3 parts. The first part of our series, inspired by Edwin Hubble, we learned about the key elements that make up our universe as we understand it today. From the physics and chemistry of stars to the study of distant galaxies, dark matter, and the structure of our universe, astronomy has made great strides in the past century when it comes to understanding the workings of these fundamental building blocks. At the same time, there are many questions that still remain to be answered. How can we explain the behavior and evolution of stars? How can we map out and study the countless galaxies that make up our universe? What exactly is dark matter, or the value of the elusive Hubble constant? And what does that tell us about the shape and ultimate fate of our universe? These questions might sound audacious, but we've learned throughout this series that they are answerable, as long as we have the right tools and imagination. During the Hubble section of the course, we also learned about the incredible importance of telescope designers and builders in the history of astronomical heroes. The Hubble Space Telescope, first envisioned by Lyman Spitzer and brought to life by Nancy Grace Roman, has revolutionized observational astronomy. The dawn of radio astronomy, made possible by Carl Yancey and Grote Reber, also drove home the value of multi-wavelength astronomy, revealing the immense value of studying the cosmos across the electromagnetic spectrum. Still, many of these triumphs can be traced back to the boldness and innovation of George Ellery Hale, the famed telescope builder of the early 20th century, who progressively broke his own records for decades as he built larger and larger telescopes. When we look ahead to the future discoveries that will help us answer our questions about what the universe is made of, we can see heroes that are continuing George Ellery Hale's legacy. Today, the largest optical telescopes on the planet are the twin Keck telescopes atop Mauna Kea on Hawaii's Big Island and Grand Telescopia Canaris on the island of La Palma in the Canary Islands. These telescopes have both made invaluable contributions to our study of some of the faintest and most distant objects in the universe, thanks to their enormous mirrors, all 3 measuring about 10 meters across, or around 33 feet. At the same time, we know that even larger mirrors can offer the opportunity to push our astronomical limits even further. This is the goal of the extremely large telescopes. The extremely large telescopes may not have the most creative names, but they are exactly what they sound like. Called ELTs for short, there are 3 different international projects underway to build what will be by far the biggest optical telescopes the world has ever seen. The ELTs are telescopes with mirror diameters larger than 20 meters. This makes their collecting area at least 4 times the size of the Keck's. The Giant Magellan Telescope, with a planned diameter of 24.5 meters or 80 feet, is being built as part of the Las Campanas Observatory in Chile. Like most large telescopes, the Giant Magellan Telescope is the result of a partnership between universities and research institutes found in multiple countries. In this case, the United States, Australia, Brazil and South Korea. Astronomers and engineers at all these institutions are working together to design and build the telescope, and when it's complete, these groups will have priority observing access. Similarly, the European Extremely Large Telescope, with a 39.3 meter or 129 foot mirror, is another enormous telescope destined for Chile and built under the auspices of the European Southern Observatory. Finally, the 30-meter telescope is exactly what it sounds like. An ELT with a 30-meter or 98-foot diameter mirror, supported by a partnership between the United States, Japan, China, India and Canada. The 30-meter telescope will also be the only ELT to be built in the Northern Hemisphere. Since the two hemispheres give us access to different swathes of the night sky, this makes the 30-meter telescope uniquely valuable as the only extreme large northern telescope. All three of these telescopes have mirrors that utterly dwarf previous generations of large telescopes. They utilize a technique that was unavailable to George Ellery Hale, combining smaller custom-shaped mirror segments to act as one giant mirror. They also feature cutting-edge adaptive optics, using lasers to measure the tiny ripples of the Earth's atmosphere, and magnetic actuators behind the mirrors to adjust its shape in real time and cancel out any atmospheric imperfections. All three scopes are also scheduled to achieve first light, the moment when a complete telescope takes its first observations of the night sky, in the mid to late 2020s. When they do, their combined scientific power will be utterly groundbreaking. Their enormous mirrors and adaptive optic systems will produce images 10 times sharper than the Hubble Space Telescope. We'll be able to clearly pinpoint and study individual stars buried in crowded galaxies hundreds of millions of light years away, probe the chemistry of the gas and dust in even more distant galaxies, and observe the motion of these galaxies in unprecedented detail to study everything from the distribution of dark matter to the expansion of the universe. At the time of recording, these telescopes are still in the design or construction phase, finalizing where they will be built, breaking ground, building the domes and support facilities, and casting, coating and polishing the all-important glass mirrors. Heroes of these telescopes are the scientists, engineers and support staff who make this work possible, as well as all those who advocate for the continued construction and support of these powerful new observatories. For the second part of this series, we turn to Albert Einstein as a unifying theme, exploring some of the incredible extremes of astronomy: high-energy stellar explosions, mind-bending mysteries of space and time, and new ways to study and understand gravity. One constant theme across these topics was the changes that are constantly churning away in our dynamic night sky. The flash of a new supernova, the brightening and dimming of a variable star, and the brief burst of light accompanying the collision of two neutron stars can act like the equivalent of lighthouse beacons, drawing our attention to exciting new phenomena happening in our universe, if we're lucky enough to spot them. An exciting new telescope currently under construction in Chile will soon be revolutionizing the way we study the changing sky. The Vera C. Rubin Observatory, named for the brilliant observer and astronomical hero who discovered dark matter. The latest successor in a long string of optical sky surveys, this 8.4 metre or 27.5 foot diameter telescope will have a single but spectacular mission. It will photograph an enormous swathe of the southern sky once every few days, over and over again, for 10 years. If the diameter of the telescope doesn't impress you, given the ELTs we've just learned about, the camera should. The Rubin Observatory's cutting-edge camera would generate images that are each 3.2 gigapixels in size. To understand how immense that is, consider a TV screen, or a laptop screen, or a tablet. Then imagine an astronomical photo rich with data from faint stars and distant galaxies, so huge and detailed that it will require 1,500 high-definition TVs to display everything. And remember, that building-size array of TVs would represent just one single image from this new survey telescope. The Rubin Observatory would generate 20 terabytes of data in a single night. So from its remote location in Cerro Pochon in Chile, it needs a way to transmit this data to servers so that astronomers around the world can see whatever new discoveries the telescope has spotted on any given night. The fibre network connecting the Rubin Observatory to its base facility at La Serena is capable of transmitting 600 gigabytes of data per second. At this speed, the telescope could transmit all 24 of these programs that make up this series in less than half a second. Getting these new data to astronomers is crucial because the sheer volume of information coming out of the Rubin Observatory will be incredible. Thanks to studying the sky over and over, it's expected to detect over 1,000 supernovae every single night. Right now we barely detect 1,000 supernovae in a year. The telescope will also build up an enormous library of data on variable stars, tracking every star in the sky whose brightness changes over the 10-year duration of the survey. With these data we should be able to pinpoint the final phases of some star lives, better understanding the physics that dictates the explosive deaths of massive stars and the formation of exotic compact objects like neutron stars and black holes. The data from the Rubin Observatory will also be an invaluable resource for spotting new asteroids and other small moving objects in our own solar system, including near-Earth objects. The Rubin Observatory will offer a wealth of new data on the changes happening in the optical night sky. But there are other future facilities that will be monitoring our dynamic universe in a very different way. During the Einstein portion of this series, we learned about the Laser Interferometry Gravitational Wave Observatory, or LIGO, the enormous laboratories built to detect the tiny space waves predicted in general relativity. LIGO observatories are mind-blowingly sensitive, detecting compressions in the fabric of space-time that are 1,000 times smaller than the width of a proton. At the same time, they face some basic limitations. They grapple with many different sources of interference, everything from trucks driving on a nearby highway to rain falling on observatory ground must be nullified so these observatories can detect tiny gravitational signals. Gravitational wave observatories may work very differently than traditional telescopes, but the solution to annoying terrestrial problems is still the same. Why not try putting them in space? The European Space Agency is currently trying to do exactly that. They have plans for the Laser Interferometer Space Antenna, or LISA. a space-based array of 3 gravitational wave detectors that will be launched and arranged in a perfect triangle orbiting the Sun along the same path as Earth. By eliminating the noise created by our own planet, the LISA detectors will be capable of detecting an entirely new subset of gravitational waves. Right now, our most sensitive Earth-based detectors are able to detect the collisions of enormous black holes, tens of times the mass of our own Sun, as faint, fleeting chirps. LISA, on the other hand, will be capable of detecting gravitational waves generated by binary orbits. In other words, it will be able to pick up persistent signals from in-spiraling black holes, or neutron stars, or even normal stars before they even collide. LISA should even be able to predict the time when the future collision will occur, ushering in a new era of gravitational wave astronomy. If we know these events are coming, then we can prepare other ground and space-based observatories in advance, training our resources on the exact spot in the sky at exactly the right time to capture the gravitational waves and electromagnetic signatures of these events. LISA is a sizable engineering undertaking, and teams at the European Space Agency are working with today's large groups of gravitational wave scientists on the ground to prepare this amazing new observatory. It's expected to launch by the mid-2030s, and when it does, it will offer a phenomenal new view of gravity and the incredible physics in our universe. The third and final section in our series was shaped around Carl Sagan. Sagan was a famous ambassador and advocate for astronomy, a specialist in researching our own solar system, and a prominent voice advocating for the study of other worlds and the search for life elsewhere in the universe. In our own solar system, astronomers and planetary scientists are still launching innovative new missions and space probes to study Earth's nearest neighbours. Rovers are hard at work on the surface of Mars, exploring the planet's surface for signs of past life, and making new planetary geology discoveries. In the mid-2020s, NASA will launch a mission to Titan, the largest moon of Saturn, which will carry a helicopter-like lander that can take off and land across Titan's surface, to study the moon's chemistry, atmosphere, and potential for habitability. NASA's Parker Solar Probe, launched in 2014, is headed for the centre of our solar system. In 2025 it will pass within 4 million miles of the Sun, and give us an unprecedented look at our closest star. 4 million miles sounds far away, but it is minuscule when you consider that the Sun is over 93 million miles away from Earth. When it comes to other planets beyond our solar system, we already dedicate our most cutting-edge astronomical tools to the search for exoplanets. Powerful telescopes, coronagraphs, and the intensive light curve surveys done by dedicated space observatories. To study these planets in detail, to do things like probing their atmospheric chemistry to look in more depth for signs of life, we'll need another new telescope, one more powerful than today's biggest telescopes, or the extremely large telescopes, or even Hubble. We'll need the James Webb Telescope. A successor to the Hubble Space Telescope was on astronomers' minds as early as the late 1980s, before Hubble was even launched. This imagined next-generation telescope went through a number of design iterations and updates, but the basic gist has remained the same. A new telescope, larger than Hubble, further from Earth than Hubble, and operating at longer wavelengths, in this case the infrared. An infrared space telescope has a wide range of scientific applications, but the two biggest take on two of the most groundbreaking scientific discoveries we've covered in these programs. First, these longer wavelengths make it possible to study incredibly distant galaxies, galaxies so far away that their light has been redshifted by the expansion of the universe to make them particularly bright in the infrared. Second, infrared wavelengths are perfect for studying exoplanets' host stars, exoplanets themselves, and all important chemical properties of these planets' atmospheres. These plans eventually culminated in the James Webb Space Telescope, named for the NASA administrator during most of the 1960s, who led the agency through the development and launch of the crewed Mercury, Gemini, and early Apollo missions. Like Hubble, Webb carries multiple instruments capable of taking infrared photographs and capturing infrared spectroscopy of everything from nearby planets to record-breakingly distant galaxies. These instruments will be gathering light captured by a 6.5 meter or over 21-foot mirror, designed specifically to reflect and focus infrared light. The mirror is so large, by far the largest telescope ever sent into space, and was launched on December the 25th, Christmas Day 2021, unfurling into a classic curved mirror shape only after it reached its final destination. For reference, Hubble's telescope is 2.4 meters or 7 feet 10 inches across. Unlike Hubble, which was launched into orbit around Earth, the Webb telescope was sent further into space, much further. It will ultimately sit near a gravitational stable point beyond the Moon, where the combined mass of Earth and Sun creates a local gravitational well called a Lagrange point, where a spacecraft can maintain a stable position. Webb will be shielded from any light coming from the Sun, Earth and Moon, keeping it cold enough to effectively detect infrared light without any errant signal interfering with the data. The combination of Webb's complex mirror and its distant position, one we can't currently reach with crewed spacecraft, made it an incredibly complicated telescope to design and launch. Hubble launched with a slightly misshapen mirror, but that error was corrected through the heroic efforts of a ground crew and a team of shuttle astronauts. Webb offers us no such option. If the telescope did not launch perfectly, reach the far side of the Moon undisturbed, and unfurled its mirror without any errors, there will be nothing we could do about it. As a result, the heroes of the Webb telescope are the team members that worked tirelessly on the ground, day after day, month after month, for years, testing everything they could test and exploring every possible scenario to ensure that Hubble's successor worked perfectly, over and over again, on the first and only try at deploying it. You've probably heard of the Webb telescope because it became infamous for its delays and budget struggles. Development of James Webb began in 1996 with an original planned launch date of 2007 and a budget of $500 million. But the budget ballooned to over $9 billion and the launch date had been continually delayed, slowed down by everything from engineering challenges to the COVID-19 pandemic. Still, the costs and delays and challenges are all part of this level of scientific research. Most astronomers agree that it's better to launch Webb late and working than to launch it early and risk a preventable failure. As we know, everything worked perfectly and the mirror has deployed, being calibrated and focused. In a few months' time from now, the James Webb Telescope will be capturing images of our infrared universe and capturing new science it's revealing about the environments and potential living occupants of exoplanets. The teams of researchers who conceived and designed, built and tested this telescope are unarguably heroes of astronomy, who have dedicated years of intense effort to give us an incredible new look at the cosmos. There are even more incredible space telescopes planned for the future. One is another infrared telescope. This one the same size as Hubble, but will be dedicated to large surveys of nearby stars and galaxies to search for huge numbers of new exoplanets. Planned for launch in the mid-2020s, this will be the Nancy Grace Roman Space Telescope, named for NASA's first chief astronomer and the woman who spearheaded the first efforts to make the very idea of space telescopes a reality. Looking even further to the future, there are astronomers today who envision a kind of mega Hubble in the 2030s or 2040s. The Large Ultraviolet Optical Infrared Survey, currently nicknamed LUVOIR. This space telescope could have a mirror as large as 15 meters or almost 50 feet across, larger than any optical telescope operating on Earth today, and take up the mantle from Hubble as the world's most powerful multi-wavelength telescope. The heroes of LUVOIR and of other future space telescope missions are still in their early stages of their respective projects and are likely facing down years, if not decades, of hard work, advocating for funding and support and taking on immense design and engineering challenges. Still, all these astronomers are nothing short of delighted to be working on such an incredible idea. It's hard to even imagine what a telescope as powerful as LUVOIR could reveal about the universe, and there's only one way to find out. In these programs we've learned about the importance of cutting-edge observatories and the amazing scientific innovations that go into making these observatories a reality. When we talk about tomorrow's heroes of astronomy, it's no surprise that it's easiest to talk about our new observatory plans. The best new research facilities can be years or decades in the making, and the groundbreaking instruments of tomorrow come out of the long days and grueling engineering challenges of today. Without a doubt, many of tomorrow's heroes of astronomy will be the scientists and engineers with the foresight and vision to imagine the new tools we'll need to study the universe, and the technical capabilities and creativity to make these tools a reality. It's harder to talk about what the new discoveries of these observatories will be, because we simply don't know. We know what these observatories will tell us about the great discoveries of the past century. We know the high-precision observations of distant galaxies or detections of impossibly minute gravitational waves will help us answer questions about dark matter or the expanding universe or general relativity. What we can't know is what else we'll find. Every time we've made a new technological leap in astronomy, some wonderful scientific surprise has greeted us. Larger and larger telescopes have shown us the far reaches of the universe. The quest for a quiet radio antenna revealed the cosmic microwave background. New surveys of the night sky uncovered neutron stars and supermassive black holes at the centers of galaxies. We likely can't imagine what new discoveries the next generation of observatories might have in store for us, but we can imagine who tomorrow's astronomical heroes might be, those new scientists who will be at the forefront of these discoveries to help unravel what mysteries they pose to us. We've heard about the great heroes of past discoveries, from Hubble, Einstein and Sagan, to innovators like Carruthers and Hale. We've met heroes like Annie Jump Cannon and Margaret Burbridge, who disentangled the working of stars, shared discoveries like Jocelyn Bell's first pulsar and Jane Lu's first Kuiper Belt object, and learned about the thousands of people who built gravitational wave detectors and flew a space probe past Pluto. We've touched on these scientists' early lives, their careers, their struggles and their triumphs. We've seen the progress made in astronomy, and the value of collaboration, enthusiasm, sheer determination and hard work. We've also learned in these programs about the importance of scientific communication and advocacy, something many of our heroes prioritized in their careers. Supporting equitable opportunities for everyone who wishes to join our astronomy community isn't just the right thing to do, it's the best way to ensure the brightest possible future of our study of the universe and for tomorrow's heroes to make it possible. As I said at the beginning, this is the final standing on the shoulder of giants. But as Terminator would say, I'll be back. So until I speak to you again, everybody please stay safe, look after yourselves, and I'll see you very, very soon.